Let's look now at an introduction to the concept of algebra. When we study algebra, we're looking at combinations of three basic components. We're going to be looking at variables, constants, and operators. Let's begin with operators. An operator is a collective term for all of the signs that perform an action, like, for example, addition, subtraction, multiplication, division. Right? These are operators. Now, there are other operators besides this. There's the exponential operator. There's the differential operator. Different operators that we don't worry about either not yet, or we don't worry about them at all in this class. But an operator is something that performs an action. This adds two numbers together. This subtracts, multiplies, divides, and so forth. Okay? Aside from operators, we're going to be looking at constants. And constants are, well, they're numbers. And we're also going to be looking at variables, which are numbers. You say, well, wait a minute, they're the same thing, they're both numbers? Well, they are, but there's an important distinction. A constant is a number that has a known quantity which doesn't change, whereas a variable, well, it's the opposite. It's a number that we don't quite know the value of and which can change. So here, a constant, these are numbers. These are unchanging. Whereas variables are numbers that can change. Now, before we look at these in the context of algebra, it's a little strange to say, okay, well, what do you mean it's a number that changes and doesn't change? How does that work? Let's consider a practical example, something that most of us are familiar with in our lives, and that's the price of gasoline. Let's say you have a car. Let's just use an example of my car. My car has a 10-gallon tank. Okay? So if you ask me how many gallons of gasoline fit in your car, I can say 10. Now, if you ask me how much is it going to cost to fill up your car, well, I don't know. That can change because, after all, the price of gasoline changes every day, or every few days at least. Yesterday was $2.05. Tomorrow it might be $2.07. Maybe it'll be down to $1.99. That's a variable. So here, a constant is something like the size of my tank of gas. That's not going to change. My car's not changing. It's not going to get any bigger or any smaller. Whereas a variable is the price of gasoline. I don't know what that is. And even if I find out what it is, it'll be something different tomorrow. Maybe, or maybe not. So that's what we mean by it. They're both numbers, 10 gallons versus $2.07. But this one, the 10, won't change, whereas the price of gasoline might. A constant, since it's unchanging, we can go ahead and write it as whatever value it is. So examples of constants are something like 2, 1/3, 0, -5. And even numbers like pi. It's a very long, drawn-out number to write out, 3.1415926535, and so forth. You'll remember this from geometry. It has to do with the circumference of a circle. But even though it's a long, drawn-out number, it's a constant number. In other words, once you know what pi is, that's what pi always is. It doesn't ever change. Variables, on the other hand, can change from day to day, from minute to minute. So what we do is we can't write down a specific value for them, which means we denote them with a different symbol. Common symbols for variables are letters from the alphabet: A, B, C, X, Y, Z, and so forth. Okay. Now, if you take a combination of one or more of these, you form an expression. So, definition. An algebraic expression An algebraic expression is made of numbers, either constants or variables, or I should say and or variables, because you can have one, the other, or both. Constants and or variables under operations. When we say under operations, we mean they're being affected by these operations. We're actually taking a constant and another constant and adding them together, or we're taking a constant and a variable and multiplying them, and so forth. So examples of algebraic expressions are something like, well, as I mentioned, you can take two constants, 2 and 5, and add them together. That's an algebraic expression. You can take a constant and a variable, 2 and x, and multiply those together. Right? That is 2x. Or you can take two variables, x and y, and you can divide those. So it can either involve constants or variables or a combination of both. Now, whenever your expression involves a variable, this we know is a number. We just don't know what number it is. And in fact, it can be several different numbers depending on the circumstances. So whenever we assign it a value, whenever we say, okay, the price of gasoline for today is $2.07, and maybe it'll change later, or maybe it'll change tomorrow, or maybe not. We don't know what's going to happen down the line. But for this moment in time, we know that it is $2.07. Then the way we say that is we are evaluating the expression. When we evaluate an expression, we're assigning a value to the variable or variables if there's more than one, and then simplifying. So here we're going to to evaluate. You see the word value in there, V-A-L-U. And we're assigning a value to it. To evaluate an expression, means to assign a value, hence evaluate, a value to each variable. If there's one, well, then you assign a value to that one. If there's several, you assign a value to each of them. To each variable, and simplify. So, for example, let's say the price of gas. Say I have an empty tank of gas, 10 gallons. All right, well, that's 10 gallons. And how much does it cost me to fill up a tank? Well, it's 10 gallons times the price. All right, if it's $2 a gallon, it's 2 times 10 gives me $20. All right, but we don't know what the price of gasoline is. Okay, well, let's say we find that today it's $2.05. Okay, then what we're going to do is we're going to evaluate this. So, evaluate for x equals to $2.05. Well, then what we would do is we would simply substitute the variable for that number. That would be 10 times $2.05, which is $20.50. Now, if later on I said, oh, well, I don't need any gas today, but I come back tomorrow and it's $2.09. Okay, well then we're doing the same thing, but we're going to evaluate for a different value. Evaluate for x equals to $2.09. And well, now it's 10 times 209, which means it's $20.90. Notice the constant never changes from problem to problem, but the variable can have different values at different times. Note that when you're dealing with algebra, you're going to have operations on numbers, some of which you may not know a value for, which means that we're going to have to find a way to add numbers, even though we don't know exactly what they are. We'll have to find ways of multiplying numbers, even if we don't know exactly what they are. We'll have to find ways of doing arithmetic, without numbers. So in order to do that, we need to be very, very familiar with how operations work. Yeah, I can add 2 and 5 if I can just count. I start off with 5 and add 2 more, and that's 7. But what if I didn't know that that was 2 and 5? What if I was told to add x plus y? What does that even mean? How do I work with numbers if I don't know what they are? So we're going to have to become very familiar with how operations work, not just for specific numbers, but in a more abstract sense. A good way to do that is to begin by dissecting how each of these operations work, and that's by looking at, and to do that, we're going to look at how they work with numbers, and we're going to take a look very, very closely. For the next few, for this section and for coming sections, we're going to be looking at arithmetic, adding, subtracting, multiplying, and dividing. But what you want to do is you want to pay careful attention not to the answers. Yeah, the answers those are important, the final result. But what you really want to look at is the process of how did we do this? What does it take to go from one step to the next to the next? Oftentimes we focus on here's the question and here's the results. But what's going to become very important is to learn what happens in each and every step and why that is the next step. Because as we go further into algebra, what we're going to start doing is we're going to start removing some numbers and replacing them with variables. We're going to start removing constants and replace them with variables. And if we're familiar with how the process works and how we know what comes next, once you replace the constants with variables, you'll still be able to do the process. All right? So here, let's take a look at numbers, constant numbers. That way, we can learn the properties of those numbers. We can learn what they can and cannot do, what we can and cannot do with them. And as we start replacing them with more abstract things, we'll still be able to carry that information to help us make sense of how variables work as numbers. All right? So let's talk about just numbers. Right? Numbers are not all the same. There are different categories of numbers which have different properties. So let's take a look at different categories of numbers. Let's begin with the most natural numbers. In fact, that's what they're called, the natural numbers. The natural numbers are the numbers that come naturally. In other words, they're the ones that you would experience in nature. Oh, I have 2 apples. I have 3 oranges. I have 5 bananas. I have 7 sticks of wood. The natural numbers are also sometimes called the counting numbers. Because they're the numbers that we learn to count. As a child, you first taught your numbers starting from the number 1. Right? And whenever you learn a language, whether it be as a child or as an adult, you learn a new language, one of the first things you always learn is the counting numbers. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, 11, 12, and so forth. There is no end to the natural numbers. There is no end to the counting numbers. There is a start. You start with the number 1. But there is no end. It keeps on going forever. The 3 dots indicate it keeps on going. Right? The natural numbers are, well, natural. They're the ones that appear in nature whenever you're counting things. Also the counting numbers. All right, now, the natural numbers do not include the number 0. You say, well, why not? I mean, 0 is natural. Well, kind of, but if you think about it, not really. Because I might say I have 1 apple here, I have 2 apples, or 3 apples, or 4 apples. And you say, well, yeah, I can have no apples. Well, that's true, but if you have no apples, you generally just don't think about apples, right? It would be like saying, okay, there are 0 hamsters on this piece of paper. That's true, but you wouldn't have thought of that unless I had stated that, and that really does seem like a strange statement. It's true, but it does seem a little strange to bring it up. In fact, the concept of the number 0 took humans thousands of years to come up with. Going off of early historical records, it seems that the number 0 was invented in India, approximately the 5th century. So that brings us to what are called the whole numbers. The whole numbers are the natural numbers and the number 0. The number 0 is not considered a natural number. It is the next stage, which brings us to the whole numbers. There is no end to the whole numbers, but there is a beginning. The development of different numbers is not something that someone sat down with and said, okay, I'm going to invent math, and so here are numbers. They show the development of how we've used and needed math throughout our history. When you have farmers and you have hunters, and you don't have cities, but everyone is nomadic. Early in human history, you have very few problems that involve math. Really, all you need to know is how much food do I have, or how many people do I need to feed. Right? So counting's enough. I have 1, 2, 3, 4, 5 pieces of food, and I have 1, 2, 3, 4, 5, 6, 7 people to feed. Yeah, I need more food. Right? But eventually, you start to settle down, and you start to trade with other people, and very quickly, you come up with the concept of money. That's where 0 became necessary. 0 became necessary when people were starting to use money and starting to keep track of debts. Oh, I have 2 pieces of money, two, let's say dollars, right? I have $5, $7. I'm owed $4. I'm owed $6. Oh, I don't owe anyone anything. No one owes me anything. 0 comes about from starting to use the use of money. Now, you notice very quickly that once you start using money, well, we can have systems of debt. We can have positives and negatives. That brings us to the next stage of numbers, and that's the integers. The integers are the whole numbers and their opposites, meaning negative numbers, -1, -2, -3, and so forth and so on. There is no beginning to the integers. They go on forever this way. And there's no end to the integers. They go on forever this way. Okay? The integers include the positive numbers and the negative numbers. Note 0 is not considered positive or negative. Right? 0 is just 0. So here these are positive. And to the left of 0, you have the negatives. And then 0 is not considered positive or negative. It's just 0. Now, again, if we're still talking about money, you start to quickly need something a little bit besides just positive and negative numbers. You start to owe people fractions of things. You start to say, well, I sold 1 cow. I sold 2 pigs. I sold 3 chickens. Well, yeah, no one wanted to buy a whole cow. In fact, I had to cut it up. I sold half of a cow. I sold a third of a pig, and so forth. Right? I sold a cow for half. So I sold a chicken for half of a pig. You start having to worry about pieces of integers. These are called the rational numbers. Rational, you see the word ratio in there. R-A-T-I-O. Ratio is just another word for fraction. So they're called rational numbers because they're numbers that include fractions. They include the ratios. And here, make a note of that. This includes fractions. Okay. So you have things like 0, which is technically a fraction because you can write that as 0 over 1. And you have numbers like 1 and -1 because, again, those are fractions. 1 over 1 and -1 over 1. But then you have all the numbers that we traditionally think of as fractions, like 1/3 and 2/5 and so forth and so on. And -1/2 and -7/8 and so forth and so on. And again, there's no beginning to the rational numbers and there's no end to them. They go on forever in both directions. Notice that every integer is a rational number because negative 2 is negative 2 over 1. And negative 3 is negative 3 over 1. And positive 4 is positive 4 over 1, and so forth and so on. So notice so far, every one of our numbers has been included in the next set. But that is not the case for our last collection of numbers here, which are called the irrational numbers. The irrational numbers are basically any number that's not rational. You say, well, what does that mean? Any number that's not a fraction. Well, you just said that every integer is a fraction, so what else is there? Decimals? Well, 0.5 is a decimal, but that's the same as 1/2, and I know 1/2 is a fraction. So what is an irrational number? Well, again, by definition, it's really just any number that's not rational. But again, what does that mean? Can you give me an example? What's an irrational number? What do you mean by a number that's not a fraction? Well, to answer that, let's take a look at what fractions look like if we consider this not as a number, but as a division problem. Let's say I have the number 1/2. Let me convert that to a decimal, because after all, I know every fraction is rational. I know every integer is rational. I'm trying to find something that's not rational. Well, every whole number, every integer, every fraction, that's already included. The only thing left is a decimal. So let me see if I can find a decimal that isn't rational. Okay, well, let's see. Let's start with the number 1/2. Now, I know when I write this as a decimal, it will be a rational number because 1/2 is rational. It's a fraction. But by doing this, we'll see what it takes to be rational, and then maybe that'll show us what it means to be irrational. So 1/2, well, let's see, that's 1 divided by 2. Put a decimal, put a 0 there. 2 goes into 10 5 times. 5 times 2 is 10, and there's no remainder. Okay, so 1/2 is equal to 0.5. Okay, 0.5. Let's try a different fraction. Let's say 3/8. Okay, so 3 divided by 8. 8 goes into 30 3 times. 3 times 8 is 24. Subtract gives us 6. We'll drop another 0. 8 goes into 67 times. 7 times 8 is 56. And we subtract that, gives us 4. Drop another 0. 8 goes into 45 times. 5 times 8 is 40. You subtract, and that gives us 0. You pick your decimal straight up, and you get 0.375. So far, we've seen two fractions changed into decimals. 1/2 is equal to 0.5. 3/8 is equal to 0.375. Let's do one more. Let's say 5 over 6. Okay? 5 over 6. Well, let's see, we're going to take 5, and we're going to divide that by 6. All right, 6 doesn't go into 5, but it does go into 50. 6 goes into 58 times. 6 times 8 is 48, and it gives us 2. And we can drop a 0. 6 goes into 20 3 times. 3 times 6 is 18. Subtract gives us 2. Drop a 0. 6 goes into 23 times. 3 times 6 is 20. And notice what's going to happen. It's going to be another 3, 3, 3, 3, 3, on down forever. So here, this is 0.8333333 on down forever. Notice these first two eventually gave me a 0 remainder. They eventually end. These are called terminating decimals. They terminate, they end. Eventually, you get no remainder. This is called the repeating decimal, for obvious reasons. It's a decimal where eventually the number just repeats. 3, 3, 3, 3, 3, 3, 3 on forever. It turns out that if you take any fraction and turn it into a decimal, these are the only possibilities. It will either terminate or it will repeat. Any rational number must terminate or repeat. So if I can find a decimal that doesn't terminate and it doesn't repeat, so that's what we mean by an irrational number. An irrational number is any number that's not rational. An example of that is any decimal that doesn't terminate or repeat. So here this is an example is any decimal that does not terminate or repeat. You say, well, what does that look like? Well, for example, 4, 5, 6, 7, 8, 9, 10, 11, 12, ... That will never terminate because you're never going to run out of numbers, and it'll never repeat because notice 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The numbers keep going up. You're never going to come back to the number 1. So this is an example of a irrational number. It goes on forever, so it doesn't terminate. And since numbers are going to keep going up, it's never going to repeat. Another example of an irrational number is one that we're all very familiar with from geometry. It involves circumference of a circle, and that's the number pi, which is 3.141592653, and so forth and so on. This number, it's actually kind of complicated to prove that that's true, but it is true. This number will never terminate, it never stops, and it never repeats. It's a little hard to show exactly why that is, so for right now we're going to state it as a fact. It's true. This doesn't terminate or repeat. If you stick with us for more advanced classes, eventually we can talk about why it doesn't. But for now, it does not repeat. When you take all of these together, the natural numbers, the whole numbers, the integers, and the rational numbers, these are all nested inside of one another. In other words, this is inside of this is inside of this, and this is inside of this. The irrationals are completely separate, though. So we could draw that as a diagram. We could say let's say you have all the natural numbers right here. Well, the natural numbers are inside of a bigger set called the whole numbers. Because after all, every natural number is a whole number. But there are more whole numbers than there are natural numbers, right? Or there are some whole numbers that are not natural numbers, rather. Okay? But then, the whole numbers are inside the integers. Because every whole number is an integer. Every whole number is an integer, but there are some numbers that are integers that are not whole numbers. So here the whole numbers are inside the set of integers. And then every integer is a rational number. So the integers are inside of an even bigger set called the rational numbers. But now completely separate from the rational numbers is a set called the irrational numbers. Because remember, by definition, irrational means not rational. So there's never any overlap. These are completely different. When you take all of this together, this whole system, the rational and the irrational and everything that's inside of them, this is called the set of real numbers. And we have a symbol for that. Instead of writing out the entire phrase, the set of real numbers, the symbol for the set of real numbers is the letter R, with sort of a double stick, sort of a double back here. This is read as the real numbers. One very convenient way of illustrating the real numbers, aside from a diagram like this, is with the number line. Because after all, the number line is, here's your 0, your 1, your 2, your 3, your 4, your 5, and so forth. And your -1, your -2, your -3, and -4, and so forth. These are your integers. Right? But then, if you go past the integers, everything in between the integers is some decimal. Okay, well, if it's a decimal, it either has to terminate, repeat, or not do either of those. Well, if it terminates or repeats, it's going to be rational. And if it doesn't do either of those, then it's got to be irrational. So everything in between these numbers, everything between 0 and 1, everything between 1 and 2, 2 and 3, all of these decimals, they're either rational or irrational. So if we consider these integers, along with all the stuff in between them, going on forever in both directions. After all, there is no first number, there is no last number. It goes on forever in both directions. This line has on it, somewhere on there, every number you could think of. You want a whole number? Sure. Starting from 0, 1, 2, 3, 4, 5, on forever. You want an integer? Sure. Here are the negatives on this side. Here are the positives on that side. You want a rational number? Like a fraction? Sure. What do you want? 1/2? That's between 0 and 1. 7/3? That's the same as 7/3 is the same as 2 1/3. So a little bit past 2. Or you want an irrational number, something like pi, 3.1415. Well, that's a little bit past 3. Every number that you could think of is somewhere on this number line. So the number line is a good way of representing the set of real numbers here. Now, by writing the set of real numbers as a number line, you introduce a concept of order. In other words, once you write the real numbers this way, you introduce a concept of, oh, this one comes sort of before this one. Right? This one comes before this one. This one comes after this one. Well, what do you mean by before and after? I mean, maybe I want to go this way. Maybe I want to start counting from here and go this way. Maybe I want to go backwards. Or maybe I want to count from here, positive, negative, like that. Okay, so we want to be more careful. When we introduce a concept of order, the way we're going to do it is we're going to do it based off of direction. The way we say it is, any number that is to the left is less than any number that's further to the right. So numbers get greater as you move to the right. Numbers become lesser as you go to the left. So here, let A and B be two real numbers. So in other words, A and B are just two numbers that are somewhere on the number line. Okay? If A is to the left of B, then we write A is to the left of B. And we say A is less than B. Okay? Notice the way I said it. If A is to the left of B, then we write A is to the left of B. You might be familiar with these as inequality symbols, less than or greater than. After all, that's the way we read them. But what these are, they're arrows. Here, A is to the left of B. Notice that's an arrow. Maybe it becomes a little more obvious if I draw the little stick inside the arrow. Right? A is to the left. Right? So it's an arrow pointing to the left. That's what those symbols are. On the other hand, if A is to the right of B, well, it doesn't take much imagination to know what symbol we're going to use. We're going to use an arrow pointing to the right. if A is to the right of B, then we write A is to the right of B, like that. It's an arrow pointing to the right. And what we say is A is greater than B. One thing to not be misled by, this is not the same as the size of a number. Right? Here, the number 2 and the number -2 have the same size. Right? They're both 2. They're both 2 steps away from 0. But here, -2 is less than 2 because -2 is to the left. Right? Here, -3 and 0. Here, 0 is, well, it's 0. There's nothing there. This has a bigger size. But if you compare the positions, this is less than 0. It has nothing to do with how big the number is. That's a really big negative number. That's a really small positive number. It doesn't have anything to do with how big it is. Greater than or less than has to do with position. Further to the left is lesser. Further to the right is greater than. So for example, let's say we have the number 2 and the number -3. Okay, is 2 to the right? So you always start by asking about the first number. You're asking, where is this one relative to this one? Is 2 to the left of -3 or is it to the right of -3? Well, here's -3, 2 is to the right. Okay, so we're going to have the arrow pointed right. And we say 2 is greater than -3. Greater than, the other way would be less than. Let's say we have -1 and +1. Okay, again, you read this with respect to this one. Or in other words, is -1 to the left of 1 or is it to the right of 1? Well, let's see, -1 is to the left of 1. All right, here's 1. You'd have to go left to get to -1. Okay, so then that's, the arrow's pointed left. It's less than. -1 is less than 1. Okay? Go ahead and try this. Let's put a few more numbers out here. 4, and let's say -4. Okay, go ahead and give this a try. Fill in the appropriate symbol, either greater than or less than. Let's see, let's do -4 and +2. Let's try -1/2 -1. And let's try 4 and 1. Okay. Fill in the appropriate symbols. Go ahead and pause if you need to. And once you have the correct symbols, go ahead and unpause and we'll confirm it together. All right, so let's take a look. -4. Notice, there's your -4. There's your 2. -4 is further left than 2. Okay, so you have your arrow pointed left, and it is less than. -4 is less than 2. -1/2, I don't have that drawn up here, but 1/2 is between 0 and 1. So -1/2 must be on the opposite side here. So here, -1/2 would be between 0 and -1. Okay, so -1/2, compared to -1, it looks like -1/2 is further to the right. So -1/2 is further to the right than -1. -1/2 is further to the right than -1. Or the way it would be read is -1/2 is greater than -1. And then finally 4 and 1. Okay, well there's 4 that looks compared to the number 1 that looks like it's further to the right. So 4 is further to the right than 1. 4 is further to the right than 1. Sure, 4 is greater than 1. Note here, -1/2 is greater than -1. Here, 1/2 is smaller in size, But that's not what we're talking about here. It's not about how big the number is. It's about its relative position, further left versus further right. Incidentally, these symbols, the greater than or less than, these are called inequalities. So the greater than, the less than, also greater than, equal to, or less than or equal to. These are called inequalities. The greater than equal to is the same as the greater than, except you also include any number that's equal to. So for example, if we were to say is 4 greater than 3? Of course the answer is yes. 4 is further to the right than 3, so it is certainly greater. If we were to ask, is 4 greater than 4? The answer is no, it's not greater than, it is 4. However, if we ask, is 4 greater than or equal to 4, then now the answer is yes. Because here, this is a two-part question. First, it asks, is 4 greater than 4? Oh, no, it's not. Oh, but the second question is 4 equal to 4? Yes, it is. Oh, okay. Well, in that case, at least one of them was fine. So then, yes, that is true. 4 is greater than or equal to 4. It's not greater than, but it is equal. So here, greater than and greater than or equal to, the only difference is this one allows the exact number, whereas this one does not. Here, 4 is not greater than 4, but it is greater than or equal to 4. Likewise, less than and less than or equal to have the same relationship. Now, I mentioned that whenever you're talking about inequalities, whenever you're talking about greater than or less than, it's not about how big the number is. It's about whether it's further to the left or to the right. Okay, but so does that mean we never worry about how big the number is? Well, no, we do. It's just not referred to as being greater than or less than. When we talk about how big a number is, we're talking about its absolute value. Definition. The absolute value of a number denoted with 2 vertical bars around the number is the distance that number is away from 0. And the absolute value is the concept of the size of a number. So if you have your number line 0, 1, 2, 3, 4, -1, -2, -3, -4. If I want to find the absolute value of the number 1, then starting from 0, I count how many steps it takes me to get to the number 1. Well, it only takes me 1 step. Okay, so the absolute value of 1 is the number 1. The absolute value of the number 4, again, I want to count the number of steps. Well, it's going to take me 1, 2, 3, 4 steps. Okay, so the absolute value of 4 is 4. Now, let's say I want the absolute value of -4. Well, starting from 0, it's going to take me 1, 2, 3, 4 steps. Notice, we never asked what direction are you taking the steps in. We're just asking how many steps. And to get to -4, I took 1, 2, 3, 4 steps. So the absolute value of 4 and the absolute value of -4, they're both 4. So even though these are on opposite sides of 0, here this one's further to the right, so it's greater. This one's further to the left, so it's lesser. They have the same absolute value. The absolute value is sort of the concept of size. How far away, how big is the number? Now, how far removed are you from nothingness? Note that because you're looking at a distance, it's never going to be negative. So here, note, absolute value is never negative. The smallest absolute value is 0. All right, because if you're at the number 0, you are 0 steps away from 0. Anything else, you're moving a positive number of steps in one direction or the other. So here, note absolute value is always positive. Oh, I guess is always 0 or positive. 0 is not a positive number. It's not negative either. Absolute value is always 0 or positive. Oh, I guess I could have just said it's always a whole number, right? Because after all, whole numbers include 0 and all the positive numbers. The absolute value is always 0 or positive. And it's okay if you have fractions in there. So for example, the absolute value of negative 1/2, if I'm starting at 0, here's negative 1/2, I take half a step back. Well, it doesn't matter if I take half a step back or half a step forward. I just want to know how many steps did I take. Okay, well, I took half a step. So the absolute value of negative 1/2 is 1/2. Notice your absolute value is always positive. Or 0. After all, if I'm already at 0, how many steps do I need to take to get to 0? Well, none. I'm already there. So the absolute value of 0 is itself 0. So every absolute value is either 0 or positive. Note that every number on the number line, except for 0, will have one other number that has the same absolute value. 4 and negative 4 have the same absolute value. 3 and negative 3 have the same absolute value. 1/2 and negative 1/2 have the same absolute value. Every number, except for 0, has a number that has the same absolute value. Those are called opposites of each other. So our last definition for now. Definition. Two numbers are called opposites if they have the same absolute value but are on opposite sides of the number line. And here I should be more specific to real numbers. You say, well, what else is there besides real numbers? In this class, nothing, but anyone who goes into our college algebra classes will see something beyond the real numbers. You worry about that if and when you get there. So here, two real numbers are called opposites if they have the same absolute value, but are on opposite sides of the number line. So for example, 4 and negative 4, or 1/2 and negative 1/2. Here, 4 and negative 4 are opposites. Negative 1/2, positive 1/2 are opposites. What's the opposite of negative 7? Oh, it's got to be positive 7. What's the opposite of positive 3? Oh, it's got to be negative 3. 0 doesn't have an opposite because it's the only number that has absolute value 0. But every other number, either to the left or to the right of 0, has an opposite. Whenever you have opposites, they're denoted with the negative sign. And that includes even with a variable. So here, note, opposites are denoted with the negative symbol. So if, for example, you were asked what's the opposite of x, You say, well, I don't know what x is. It doesn't matter. Its opposite is negative x. Now you say, okay, well, sure, that makes sense. The opposite of a positive is a negative. Well, we don't know that x is positive. It's a variable. Maybe x is 4, which means that its opposite is negative 4. But maybe x is negative 7, which means its opposite is positive 7. So here, this negative doesn't mean that this is a negative number. All it means is that it's the opposite of this one. So be very mindful of that. If it's a constant, well then sure, it's either a positive constant or a negative constant. But when you have a variable, that doesn't mean that this variable has to be positive and that this one has to be negative. It could be that this one's negative and this one's positive. That negative doesn't tell you the sign of the variable. It simply tells you that these are opposites. Note, negative x does not have to be negative. It just has to be the opposite of x. So if x is positive, then negative x is negative. But if x is negative, then negative x must be positive. It doesn't have to be negative. It has to be the opposite of this. And with that, we come to the end of this topic for now. Note that this is mostly a vocabulary lesson. We didn't have many examples here of anything other than here's what we mean by this word, here's what we mean by that word or by that expression. If anybody has any questions on any of this vocabulary or what any of this means, please make a note of that and reach out to me. And I hope everyone has a nice day.